This is lecture 10 of Machine Learning and Bayesian Inference. I've been talking about some more practical issues in the last couple of lectures, but now I want to return to talking about supervised learning. And in particular, I want to talk now properly about the Bayesian approach to supervised learning, which I'd kind of set up when I talked about the Bayes optimal classifier, but then I put it aside to talk about some other things for a little while. Now is the time to return to that. So let's just initially look at what the take-home messages might be from our discussion of support vector machines, and just remind ourselves of why we want to look further than that in some circumstances. Support vector machines can be regarded as a state-of-the-art method, again, in the context where you don't have absolutely huge data sets and where deep learning might not be appropriate. You are using the kernel trick, which in itself is a nice idea and a very old and long-standing one, although the full machinery of SVMs is more recent. And you're doing that in order to get a nonlinear model, but with a fundamentally linear underlying approach, which makes the mathematics quite nice and amenable. And you can do that without invoking the full machinery of the Bayes optimal classifier. So why might we want to use, well, not strictly speaking the Bayes optimal classifier, because as I've already mentioned, you often can't compute it exactly, and the best you can do is get an approximation to it. But why might we want to use that approximation to it when we know that it won't necessarily outperform an SVM in terms of accuracy or F1 or Matthews for a real data set of interest? Well, one reason is that it can still be extremely effective, and you won't know in practice for your data set what the best method is to use without trying a whole bunch of them out. But there are some other reasons. Firstly, I suggested when talking about the whole Bayesian approach to inference that one of its attractions is that it keeps you honest, in that it forces you to specify things like prior distributions on parameters. And we saw how this can be a useful thing when, for instance, I derived the fact that if you are minimizing sum of squared errors within a probabilistic framework, then you can think of there being an implicit assumption that the noise on your data is normally distributed. Okay, this is an assumption that was uncovered, and it's the sort of thing that you might in practice actually want to know. Okay, so setting things up within a Bayesian framework forces you to specify such things in advance. So it's keeping you honest about what assumptions you're making. Second thing here is that by actually keeping things in this full-on probabilistic framework, we might get some other things that are useful to us. The usual selling point for this Bayesian approach is that we can often assign confidences to our predictions. We don't necessarily just say it's in class 1. We might say it's in class 1, and here is a quantified level of certainty that we have about that. I'm going to talk mostly about regression for reasons that I'm going to come on to in a moment, and there we'd say, well, I predict that this is the value of the function at the new point I'm trying to do regression with, and here is a measure of my certainty about that. Sometimes you might want those certainty measures. There's also a further selling point here, which is that in this full-on probabilistic framework, you can also get alternative justifiable methods for approaching the choice of hyperparameters. But I'm getting ahead of myself. I need to do this a step at a time. At this point, it's worth just rewinding a little bit and reminding yourself of what I derived at the end of the section when I was talking about the Bayes optimal classifier. And that's on slide 69 here. The key idea, and I derived this for classification, but but we're going to move on to regression in a moment. There's really not much difference, well, if any difference at all, in the form of the equation. What we came up with was the idea that rather than just picking a single proposal for the relationship between your feature vectors and your label, which is what a lot of classical algorithms do, we were actually averaging over all of the possibilities for that relationship. Okay, so the idea is that we have a posterior probability attached to each of them. Okay, if my neural network, or whatever my method is parameterized, as in the second of the highlighted equations here, the integral version, then any setting of parameters will give me some relationship between feature vectors and labels. Rather than just picking one, I have a posterior distribution that tells me how likely each of them is in the light of the data, which is this chap here. And I average over all possible relationships, but weight according to how probable they are according to the posterior distribution. Okay, so that's done by the likelihood here, which is just giving me the probability for a class if W is the weight vector that corresponds to the relationship that I want, and X is the new thing that I'm trying to classify. Okay, so that integral is just an expected value, and the sum in the first of those highlighted equations is also just an expected value. We are taking into account all the possibilities for the relationship between feature vectors and label, but we're weighting them according to how probable they are in the light of the training examples that we've already seen. Okay, this is the key idea. So in order to actually ground this in a specific kind of supervised learning, let's say we are going to use a neural network. Okay, we're going to use a multi-layered perceptron, just as we did at the end of the artificial intelligence course last year. So we have this feed-forward layered structure of perceptrons, where let's assume that we're using sigmoid activation functions, and the output node would be either a linear activation function or a sigmoid. This gives us a neural network that computes a function h of x, x being the inputs. That function depends on the weight vector w, as always, which is the collection of all the parameters in all the nodes in that network. And in order to train this thing, as usual, okay, nothing is changing yet, we have a collection of m labelled examples with the feature vectors x sub I for I 1 up to m, and the labels y sub I for 1 up to m. Okay. It makes sense for us at this point to split that S into a vector Y of labels and a matrix X of feature vectors once again. Okay, that's just a notational nicety that makes things more amenable when we try and write down some actual derivations. Now, I'm only going to consider the regression case where the output of our network is a real number. And the reason for that is that, yes, you can do it for the classification case as well, but it's another level of complexity, okay? At least when addressed from the perspective that I'm going to show you. Once again, I have to offer my apologies. There are other ways in which you can approach the derivation of supervised learning algorithms within this framework, but in 16 lectures I don't have time to talk about them all by any means. Take this as a taste of what the field looks like. The equation that I derived earlier, and which I just gave you a quick refresher on, is this one, which was for classification. And we would, assuming that we could evaluate that integral, we would choose the class C that maximizes that probability, the probability of C given x and s, where x is the new thing that we're trying to classify, and s is the training data that we've seen. For regression, in fact, the Bayes optimal classifier or derivation turns out to have essentially the same equation defining it. Okay, it's this guy here. Okay, we still have the posterior density of the weights conditional on the training data, and we still have the likelihood. It tells us the probability of a particular output value if we've used a particular weight vector W as our underlying model, and X is the thing that we want to attach a value Y to. Okay, so the one thing possibly to add here is that what we're getting, okay, now in the regression case here, is a probability density. Okay, we're not just getting a single value out of this when we plug a new X in and say, what label should I assign to this new X that we may have never have seen before? The X now is being plugged in here, and again, assuming that we could evaluate this integral, this is yet to be seen, we would end up with a probability density on the possible label and not just one specific value. Okay, we would end up in the usual way with some probability density, which may have any shape that we like, essentially. Okay, this is where the idea of now assigning a confidence to our prediction in some kind of meaningful way comes from. If I have, for example, density for the prediction Y given W and X that looks very peaked, I may predict this as my actual output value and say, well, because this density is fairly peaked, I'm quite certain about that. If, on the other hand, I end up with a density that is kind of like this, I may predict this value, but I'd probably also say, well, I'm not really very certain about that at all, given what this distribution looks like. Okay, so that's just a slight look ahead to how this could end up being useful. Okay, but the key final thing to point out here is that the posterior and the likelihood are things that we've already seen. Okay? Can I convince you of that? Well, I'll try and convince you of that in a minute. But before I do, there are a couple of other kind of subtleties here that I need to point out about the exact way in which we're going to approach this. The first is that, okay, I started this whole discussion really with the idea that you would have a probabilistic model of your data, and that you would use that probabilistic model of your data to derive learning algorithms. And part of that was that the first thing I did was to say that you would regard your data as being generated by taking samples that are independent and identically distributed from some joint distribution on the label and the feature vectors. Okay, P of X and Y in this case. And then I put that into a context where I would have a function that was the relationship between the feature vectors and the labels, and I would add some noise to the labels, and then I would do the generating process and only show you the data, and it was down to you to work out what the function was that I'd used. Okay, that's then led to the maximum likelihood and the maximum a posteriori learning algorithms, and that's all well and good. What we're doing now is potentially more sophisticated, okay, because instead of just trying to guess the function that I used to generate the data, I'm suggesting that you should average over all of the possibilities depending on how likely they are in the light of the data that you've seen. Now, it turns out that if we try and go the whole way with this and speak about generating data in that way, in particular if we try to incorporate the density for X into our modelling, then things get very complicated indeed. Now, as a result, what we do now is regard those as being fixed rather than generated at random. The labels are still generated at random, but the x's are fixed points and are treated as such. Now, that means that, strictly speaking, and I think I've probably mentioned this sort of notational subtlety before, you shouldn't write them within these probability expressions because they're not random variables. Okay, they're now fixed. They're not being drawn according to some probability distribution anymore. So, strictly speaking, I shouldn't be writing that because x is no longer a random variable. It's just a point. If I do that and leave out things that aren't random variables, it tends not to be greeted with great joy and happiness, because it just looks odd to leave out something like x, this new point I want to classify, when everything clearly does depend on x. So the solution is to come up with a slight notational piece of trickery and to use this semicolon so that you know that y and w are both random variables, but x is some fixed vector. Okay, so two things there. One, there's just a notational trick going on so that I can keep things like x in the expressions, even though they're not random variables. And two is the fact that the actual density p of x of the feature vectors isn't being modelled here. We're just regarding feature vectors, whether they're in the training set or whether they're new things that we're trying to classify, as being fixed. And it's worth at this point just rewinding a bit and reminding yourselves of some of the expressions that I derived earlier on. In particular, back here on slide 43, I talked about the likelihood of the training set given a particular weight vector. Okay, this was derived in some detail, so it's worth just going back and reminding yourself of how that works. I also then went on to talk about what happens if you bring a distribution on the weight vectors into play. So here on slide 48, I introduced the idea of having a prior density P of W for your weight vectors, which at that point I was taking to be a normal distribution. And then I spoke about combining that with the likelihood of the training set to give you this posterior density, the probability of the weights given the training data, okay, which has now come up again. It's one of the things in the integral. But it's worth at this point looking back to see exactly how those were derived and just reminding yourselves before we move on any further. Coming back to the present, it's worth just considering what that posterior density of the weights conditional on the data is actually telling you. We have this equation now, okay? Just slightly modified once again because we're no longer considering the feature vectors, the x's, to be random variables, okay? Otherwise, other than that, everything just goes through in the same way. And as usual, this is just a consequence of Bayes' theorem. Okay, the probability of w given y is the probability of y given w multiplied by the probability of w and then normalized. Okay, hence the proportional sign. Okay, but what's important to note about this is that if you look at how this expression behaves, it typically starts off wide, assuming your prior P of W is a reasonably non-committal kind of density, like some kind of, a wide normal distribution, for example. And as you see more actual data, that density narrows down. Okay, the posterior density, the probability of the probability of W given the y's and the x's, becomes more and more peaked. Okay, which is what you would hope for, because as you're seeing more and more actual labelled data, you're getting more information about what underlying function may have been used to produce it. Okay, some weight vectors will be very unlikely to have produced the training data you've seen, and they're going to get a correspondingly low probability in the posterior density. Okay, now if we actually plot that for some, admittedly toy data in the classification scenario, this much is extremely clear. On the top left here, I have 5 training examples in 2 dimensions for a 2-class classification problem. On the top right, I have a wide prior density P of W. And on the bottom of this diagram, I have the likelihood probability of Y given W and the posterior probability of W given Y after we've seen those 5 training examples. And you can see that both of them have become quite peaked. Certainly the posterior density has become quite peaked with respect to the prior, and if we see more and more data, we'd expect it to become more and more peaked. And the reason for that is, once we've seen some data, we can basically exclude functions that are very unlikely to have produced it in the first place. So what do we need to do now? Well, we need to remind ourselves of what the 2 expressions inside that integral look like. The likelihood and the posterior density of the weights. Well, the second you have just done, I hope, because I hope you did rewind and remind yourself how that was derived. The first, well, it's part of the derivation of the second, okay? It's just that here, and in the integral that we're interested in, it's being applied to a single example, which is the new thing we're trying to classify, okay? And in producing the posterior density of the weights, the likelihood corresponds to the whole training set, okay? So they're actually corresponding to some different pieces of information. Okay, but I emphasize, if you haven't already gone back and looked at the derivations of these things, because they're exactly as they've been seen before, go back now and look at where these 2 expressions come from, because they're the same as in the earlier lectures. Do it now. Do it now. Have you done it? Good. The third thing we need is to actually try to evaluate the integral, which is where the fun starts. Okay, so let's just summarize what step 1 and step 2 look like now that you've refamiliarized yourself with them. We're talking about the regression case, so we're going to stick with the assumption that noise is Gaussian, and all the usual caveats apply. That may or may not be appropriate. Okay, but we're going to stick with that because it lets us actually derive something interesting and useful. So, the model of how we generate our data is that H sub W is our neural network, X is something to be classified. I'm going to say classified even though it's regression, okay, because it's just easier to say, and I will assume that you understand that when I say we classify X, what I mean is we're assigning a real number Y to it. So we use W to get a relationship, we plug X into that, and then we add some Gaussian noise, okay, epsilon, in order to get the label Y. Nothing has changed there. We have an extra parameter, which is the variance of the noise. This is, of course, a hyperparameter, so we'll come back to that later. Okay, but that gives us this expression for the likelihood for some new example x that we want to classify, given that we think w is the correct bunch of parameters to give us the correct relationship between feature vectors and y's. Okay, and I should emphasize again that this is not just a function of the turns x into y, it's an entire density on y. Now, the hyperparameter is traditionally rewritten as beta equals 1 over the noise variance. Okay, this is pretty standard in the literature, so I'm going to stick to it. Don't be fazed by it. It's just an alternative way of writing it, and it makes some of the later expressions look a little bit tidier. That's the entire extent to which you should worry about this. Okay, beta is just essentially a different name for the hyperparameter. And that gives us a likelihood that looks like the expression in the box. I have left out the 1 over root 2 pi sigma sub n squared, and as always, I'm doing that because we're dealing with probabilities, which means that these constant factors that are there simply to make them, in this case, integrate to 1, we can gather up and deal with later on. Okay, as long as the final result that pops out is a proper probability density or distribution, then we're happy. Okay, but we can talk in terms of things being proportional for as long as we like, as long as the final step is to make everything properly normalized. Okay, but the boxed expression here is the first of the two expressions that appear as the integrand. For step 2, once again, we're doing the same thing. This is an expression we've just recently discussed, the posterior density of the weights given the training data. In exactly the same way as before, the likelihood of the labels given the weights looks like this. Okay, we have our old friend, the sum of squared differences between the ith feature vector and the ith label yi. Now, once again, it is standard really in the field when talking about this approach to supervised learning to rewrite this in terms of the error that we've been talking about all along. Okay. The beta that appears in here is the same as on the previous slide because we're still talking about a likelihood. We still have a noise variance. And in order to combine that with a prior, we're once again going to assume that it's a normally distributed or normal density prior with a symmetric covariance matrix. In fact, a diagonal covariance matrix with variance in all directions just being sigma squared. And again, this initial variance for your prior on the weight vectors is a hyperparameter, and it's traditional to actually write alpha equals 1 over that variance and use it as a hyperparameter. So combining those two, we get the final box expression, which, again, it's nothing really different to what we saw in earlier lectures. Is the density of the weights given the training data, and it is 1 over, once again, some constant in order to normalize things. And we have this expression here, which should look very much like an expression from earlier, because it involves the error that we're trying to minimize in the traditional approaches, and also this weight decay term that I talked about at some length earlier on. Okay, so that's the second part of the expression in the integral. Now, just as a further little aside, if you look at the main part, okay, the important part of the posterior density of the weights, you have this term for the error on the training set, and you have a term that corresponds to the prior. Now, hopefully you can see that as the number of examples increases, okay, in the final boxed expression here, the number of examples increases, meaning that this part of the main section of the expression, which is the sum of squared errors, is likely to get bigger because we're just adding more and more examples into that sum. Okay, so the part corresponding to the likelihood increases, but the part corresponding to the prior remains fixed. And once again, we get this effect that for small training sets, the prior dominates. Your prior assumptions about what W should be the dominant part. And as M increases, as you see more training data, the likelihood takes over, and the training data that you have has more of an effect on the predictions that you end up making. So, we put these together. This is step 3. And we have the integral of interest. Okay, once again, the proportional sign here, okay, I've dropped out this normalizing section part here because we can just deal with it at a later time when we've done all our derivation and we just want to make sure that our density normalizes as a density again. Okay, so the proportional sign here is because we're allowing ourselves to do that. And what we've left in this integral are just the parts of the likelihood and the posterior that depend on W, okay, because it's an integral over W. Now that is the integral that we want to evaluate to give us a posterior density for Y, given the training set and some new X that we want to put a classification on. Okay, this is the integral I started the lecture with. But unfortunately, given the setup that we have so far, with these assumptions of Gaussian noise and normal distribution for the prior on the weights, there is no closed form solution for this integral. Okay, so now we have a problem. But it's one that we can quickly set about trying to find a solution for. And it's not just a problem that's restricted to this particular formulation. It is very often the case that if we try and do this kind of inference in a Bayesian framework, we end up with an integral of this kind that doesn't have a closed form solution. The closed form solution versions are very much the exception and not the rule. Okay? As a result, there is a massive and burgeoning research area on how to come up with good approximations to this kind of integral. Invariably, we have an integral that looks like the one in the box. Okay? We're taking an expected value of some function f of w with respect to a probability density on the weights conditioned on the training data we've seen. We pretty much can never come up with a closed form solution to this integral, and so there are essentially two approaches to trying to find an approximation that's tractable and that gives us results that are close enough to the actual value of the integral that they can be used effectively. The first way in which we can address this is that we can try and find an approximation to the posterior density on the weights that makes the product in the integral into something that we can actually integrate, but doesn't have too much ill effect on the actual value of the outcome. Okay, so that's the first method that I'm going to give you an example of. There are many ways of doing this, and I'm going to give you one of them. The second possibility is to make what's called a Monte Carlo estimate. Now, Monte Carlo methods will give you something arbitrarily close to the correct value of the integral, and their approximation will get better the longer you're willing to wait. Okay, so there is a trade-off here. Do you want a closed form solution that you can calculate that is good enough in that it's sufficiently close to the value of the integral, or do you want something arbitrarily close to the right value with the proviso that you may have to wait a long time in order to get it? So here is one method for changing the integrand in such a way that you make this integral tractable. And this is going to need several steps. And the first step is to find what's called a Gaussian approximation to the posterior density in the integrand, okay, to this guy. And in order to do that, we want to find a Taylor expansion of this section. And I'll come back in a moment to why we want the Taylor expansion of that section in particular. Okay, so that's the second box. Okay, we want a Taylor expansion to that expression. Now, a Taylor expansion is an approximation to a function, and we're hoping that when we plug it in, we'll get something that's good enough that when it ends up making the integral tractable, we still get decent results. I'm hoping, as I often hope, that you will recall the idea of a Taylor expansion from NST Maths. As usual, if you don't, then now is the time to go and remind yourself. But a Taylor expansion is taken around a particular point. In this case, we're going to take it around the maximum a posteriori value for W, okay? Again, the same map value that we derived earlier. The same maximum a posteriori value that we can obtain using gradient descent or any of a number of other methods for the training algorithm, okay? The reason for wanting to make a Gaussian approximation is that it does get us closer to being able to use a standard integral in order to get our approximation to I, but I need first to remind you, I think, of how Taylor expansions work. So in one dimension, okay, let's start in what's probably the most familiar case for you. If I have a function f of x and I want an approximation to it, I can pick a point at which to start my approximation. That's x naught. And then, depending on how accurate I want my approximation to be, I can decide on a particular number of terms, in this case k, to include in my approximation. And the form of the approximation is straightforward. Okay, down the right here in this box we have successive derivatives of the function evaluated at the point we're expanding around. And then we basically just have these polynomial terms, x minus our expansion point, x minus the expansion point squared, and so on. Okay, so it's a straightforward expression. Now, just take note of one important thing here. We're actually interested in the posterior, okay, which is this entire chunk. And that is e to the minus the function that I'm going to take the Taylor expansion for. Now let's just see what effect that has. Okay, we're trying to approximate something that looks like this. E to the minus f of x. So let's actually look at what happens if we try and approximate e to the minus f of x using a Taylor expansion for f of x. Okay, here I'm just going to use this specific function for the purposes of illustration. Okay, now on the left I have the function f of x. On the right I have the function e to the minus f of x. And hopefully it's clear that what the exponential does is hugely emphasize small values of f of x. Okay? We're essentially using the fact that the function we're interested in approximation is of the form e to the minus f of x to narrow down the bits of f of x that we actually have to model accurately. Because the e to the minus f of x is then going to very heavily emphasize parts of f of x that are small. So what we have here is the actual plots of f of x and e to the minus f of x. Let's now actually take the Taylor expansion of the minus f of x part about its maximum, which in this case is about 2.14. Okay, so minus f of x has its maximum around here. And look what these curves look like when we actually take an approximation using the Taylor expansion. Here I've got the approximations for k is 1, k is 2, and k is 3. If I look at k is 1, that's not a particularly great approximation. I'm just making a linear approximation to minus f of x. Okay? But if I look at the approximation for k is 2, well, okay, that's actually starting to fit the curve for minus f of x around the point where it's at its largest. Okay, and therefore around the point at which e to the minus f of x is going to be accentuating the important values. If I take the Taylor expansion for k equals 3, I get a little bit of a better approximation, but we can see we now might have problems going off in this direction. But if I look at the k equals 2 approximation of e to the minus f of x, I can see that the Taylor expansion version is actually incredibly close in this one-dimensional example to the actual function that I'm trying to approximate. Okay? So, just to recap that, I am interested in getting a new approximation to the stuff in the big box here, okay, the actual posterior density of the weights. That is of the form e to the minus f of x, where, or in fact e to the minus s of w, if I use the language on this slide. Okay, it's e to the minus s of w. And I want to take the Taylor expansion of s of w around its maximum point. Okay, which is the maximum a posteriori weight vector. And the reason for that is that the exponential, when we then take e to the minus Taylor expansion for s of x, is emphasizing that part of the function. And because this is part of an integrand and it's areas that we're calculating essentially, if the approximation gets things right in the important areas, then we can expect, we hope, to get a good approximation to the real integral. Okay, if this is the approximation to e to the minus f of x, and this is the actual value, and these are getting plugged into part of an integrand, then hopefully we're not having too much ill effect on the actual integral itself. Now, of course, the example I've just given you is in one dimension, and as usual, we're working in multiple dimensions. So we need the Taylor expansion for, we need the multivariate calculus version. But as is generally the case, in multiple dimensions, it looks like the obvious extension, okay, of the one-dimensional case. and in particular in the boxed expression here. Now I'm taking a Taylor expansion, and I'm only going to write it for this, the k equals 2 case, okay, and in this case it looks as follows. Our f of x, where x is now in more than one dimension, looks like f at the point we're expanding around, plus, okay, now this is really just the same as before. This is x minus the point we're expanding around, and this is the first derivative of f of x evaluated at the point we're expanding around, okay? The first derivative, once again, of f of x is just the vector of derivatives of f with respect to the individual elements of x. Okay. The second part of the approximation then has the second derivative of f of x, which is now a matrix, evaluated at the point we're expanding around, and now we've got x minus x minus the expansion point, but in the version that corresponds to squaring that. Okay, but when we're talking about vectors and matrices. Okay, so the gradient is as previously defined, and the second derivative is now matrix as previously defined. Okay, and this is just, once again, the obvious extension of the one-dimensional case. Now, in fact, because we're choosing a particular point to expand around, this simplifies slightly. Okay, we're taking the Taylor expansion of S of W from a couple of slides back, which is on the left-hand side of the first box here. We're using the maximum a posteriori point as the point to expand around. Now, that minimizes S of W. Okay, so the first derivative is 0. Okay, the definition of the maximum a posteriori solution is that it minimizes S of W. So the first of those terms for the Taylor expansion is now 0 and it just disappears. And this expression is actually now quite amenable. Okay, we know what S of W is. We can find the maximum a posteriori solution using any algorithm we like. And now this approximation just involves S evaluated at that point, plus an expression where the only thing that's even remotely going to be tricky is this second derivative matrix A, okay, which is this chap here. So what are we going to do with that? Well, we can actually simplify that a little bit. Okay, it's the second derivative of S of W. So in the second shaded box on this slide, it's been written out in full on the left. In the sum here, okay, the second derivative will be applied to each part of that sum separately. So on the right here, we just have the second derivative of our usual error function. I'll come back to that in a moment. And here, we're just going to have alpha I. Okay? Now, I think I'm going to leave that as an exercise. Once again, this is just like any other kind of calculus applied to vectors and matrices. If you write the mod of W squared out in full and differentiate it twice with respect to its ith and jth elements, you will find that everything collapses to a 0 or a 1, and you can write the outcome like this. Okay, so A, the second derivative matrix, now is straightforward. We already know how to calculate the first derivative of E, okay? And in fact, the second derivative can be done essentially using a further layer of backpropagation if you're doing gradient descent and doing this with neural networks. And in any case, Generally, if you can compute the derivative of E of W, where E is some error measure, then you can compute the second derivative of it as well. Okay. So, we actually already know about how to get WMAP. You can use something like backpropagation. Backpropagation will extend quite happily to give you the derivative of S of W here. And because backpropagation gives you the derivative, you can use any optimization method based on the derivative to get you the maximum a posteriori vector. And the second derivative of E of W can be obtained essentially in a similar way. So that's quite a dense lecture. Let me just quickly recap the point at which we find ourselves. We are trying to evaluate the integral at the top of this slide, okay, because that gives us what we want as the Bayes optimal regression in this particular set of circumstances. Okay, if it's a neural network and we're assuming the noise is Gaussian. The likelihood, the first factor in that integrand, and the posterior density of the weights, the second factor in that integrand, are exactly as they were in earlier lectures. Okay, we know what form they take. We've just rewritten things a little bit so that the hyperparameters, which correspond to the noise variance and the width of the prior on the weights, are now labelled as alpha and beta. Okay, but these expressions are familiar to us. Using those familiar expressions, there's no way of evaluating the integral. So what we're trying to do is initially find an approximation to the second of those factors in the integrand, the posterior density of the weights, and we're exploiting the fact that it has the form e to the minus f of something, or e to the minus f of w in this case, to allow us to take a Taylor expansion of the interior part of that expression and rely then on the exponential part to emphasize small areas of that function so that the Taylor expansion actually helps us to get something that we hope will be quite accurate. And then the final thing is that in order to take the Taylor expansion, we need to take it around a known point. So we're going to use the maximum a posteriori point, and we know how to calculate that. And the methods used to calculate that can be easily extended to calculate the second derivative part that we need as well, that's in the Taylor expansion. Okay, so as I say, a dense lecture, but hopefully an understandable one, and I will continue with the approximate evaluation of this integral in the next lecture.